This video is for Module 7 of CS33, Introduction to Data Structures and Algorithms, Part 2. This is the third installation out of 4 videos for Module 7, where we will discuss about transform and conquer. So this is a little bit better compared dun sa first design strategy that we introduced, which is yung brute force or exhaustive search. The transform and conquer approach is actually divided into 2 parts. The first stage is the transformation, and then the second stage is conquer. Okay, so this is different from the divide and conquer approach kasi for the divide and conquer approach, meron pa rin divide and conquer, yun yung first stage niya, and then may merging process pa. Pero for transform and conquer, single iteration lang yung transform and then conquer. Okay, so to give you a general idea, group of technique siya that solves a problem by transformation. And yung transformation is divided into 3 types. The first type is instance simplification, the second type is representation change, and the third type is problem reduction. So, yung difference ng 3 transformations ay yung tinatransform. So, for the first type, yung instance yung tinatransform. We are modifying or transforming the input instance, and yung transformation makes sure na simplified na yung input instance. So, when we say input instance, it's the way how the input is presented. So, sometimes the input instance can be a rearranged version of the original instance. Pwede din another way how it is written. So, that's the first type. And I will give an example later on dun sa mga type of instance simplification. Okay? For the second type of transformation, the way how we represent the instance naman. So, hindi same instance pero ang nagbago is how you represent it in the computer. So, yung binabago dito is the data structure that holds the same input instance. Okay? And then for the third type, ang binabago dito is the problem. So, we are transforming one problem to another problem na pwede nating magamit yung existing solution for that problem. Okay? So, again, it's transform then conquer. Yung ginagawa for instance simplification is to transform the input instance, and then for the simpler version of the instance, we conquer the problem. Okay? For the representation change, we transform how we represent the same instance using another data structure, and then we conquer the problem by using that different data structure to represent the input instance. And then for the third one, we transform the problem to another problem, and then we conquer the second problem, okay, kung saan na-reduce yung problem natin. That's the problem reduction. I will give at least one example for each of these types of transformation. Okay. So let's start with the simplest one, the instance simplification. Okay. For instance simplification, okay, we solve a problem's instance by transforming it into another simpler or easier instance of the same problem. So, yung ginagawa most of the time for instance simplification is to include sorting. So, may tinatawag na pre-sorting. It's pre-sorting kasi we sort the input instance before we conquer it. So, merong impact na nagagawa yung sorted input instance compared doon sa original instance na walang sorting. Okay? We can utilize algorithms that assumes a pre-sorted input instance. So, yun yung advantage ng pre-sorting. And sometimes, pre-sorting is also regarded as a pre-processing step before we conquer the problem. For the search problem, the naive method is to check each position of the input instance, and then we can have a running time of O of n, checking each position given yung search key. So, if K is in S, of course, we can identify na nandito siya sa, let's say, last part, no? And if K is not in S, kailangan niyang daanan pa rin hanggang sa dulo to say that K is not in S. That's for the naive solution. Pero, we can have an improvement of the naive solution if we can utilize a pre-sorted version of S. So, what we can do is to follow the two-stage process of number 1, sorting, and stage 2 naman is the conquering part. For the stage 1, we sort the array by an efficient sorting algorithm. And then for stage 2, conquer the problem by utilizing binary search. Okay? So, the binary search is only applicable for pre-sorted input instance. That's why necessary mangyari yung stage 1. So, the running time of the transform and conquer approach for searching is the running time of the stage 1 plus the running time of stage 2. The running time for sorting is n log n, and the running time for binary search is log n. Okay? But, since 2 stages yung kailangan nating i-assess, which is yung transform plus yung conquer part, the total efficiency or running time for this algorithm is n log n plus log n, which is bounded above by n log n. So, ang running time niya is n log n pa rin. Okay. So, the question is it good or bad? With respect to what ba? With respect to the naive solution, which is O of n, or we can say theta of n, mas matagal mag-run yung transform and conquer na n log n. Okay? Pero, in the long run, important na gamitin yung transform and conquer because most of the time, we search for the content of a list, a directory, and so on. So, we perform sorting in the initial stage. Pero, most of the searches is done in log n instead of doing it all the time. So, every time we search, you need theta of n. Compared sa most of the time, we use log n. So, if we have a list na very, very dynamic in nature, of course, hindi appropriate gamitin yung transform and conquer kasi you also need to sort it from time to time. Another example is the problem of solving system of linear equations. So, the input here is the system of linear equations that is represented by an augmented matrix. Matrix for the coefficients for this part of the equation, and the column here is for the right side of the equation. So, for the algorithmic strategy that uses transform and conquer, we will not conquer the problem using this matrix. Okay? So, the way how we do it is by transforming this version of the augmented matrix to a simpler version of the augmented matrix na upper triangular na lang, so that you can perform backward substitution with this specific format. So, the transformation here is this from this matrix to this matrix. This one is a simpler version of the instance, and then conquer this matrix by backward substitution. And then you can solve the problem using backward substitution. Representation change is the second type of transform and conquer. From my previous description, we are transforming the data representation. So, to illustrate how representation change is used for search problem, recall lang that we have an input, a multi-set, S of keys and a search key K. And then the output is, if K is in S, the location of K in S. So there are different ways how to solve the search problem. And in fact, pwede natin siyang tignan with respect to the representation used. It can be an algorithm for searching that uses lists. So for list searching, generally it's good for static data. So there are existing algorithms that uses lists. One example is the naive approach, which is the sequential search, and the improved version of it is the binary search. Okay? So the binary search is used for pre-sorted input instance. For the second group of searching algorithms, the data representation used to store the input is using a tree. So there are different types of representation for tree searching. And these are binary search trees. May mga tinatawag din binary balanced trees, which are examples are AVL trees, red-black trees, multi-way balanced trees, and so on. So medyo marami pa yan. If we change the data representation to a hash table, then the manner of searching for a key in a set is by using the hash table. So there are two different ways then of using a hash table. We can use open hashing or closed hashing. And I guess na pag-aralan na natin ito during CS32. So, why is it important to show you this taxonomy of searching algorithms? Okay. For representation change, changing the way how we represent the input instance changes the algorithm. So, depending on the scenario, kung saan natin gagamitin yung search problem, we can identify which is more appropriate. So for static data, as I said a while ago, okay lang gamitin yung list searching. For dynamic data, that is, from time to time, laging may mga changes yung sequence natin, then tree searching is better to use. So yung succeeding slides ko, I will discuss about binary search trees and yung isang example ng isang binary balanced tree, which is yung mga AVL trees. Okay, so for the binary search tree, it's just a binary tree, pero it is used for search. Okay, so the binary tree here is with extra property. Okay, so may tinatawag na binary search tree property. Everything on the left side of K is less than K. Everything on the right side of K is greater than K. Okay, so for example, I can create a binary search tree for this numbers 5, 3, 1, 10, 12, 7, 9. I wanted to store it in a binary search tree. This one is a binary search tree because for every possible node in this structure, it obeys this property. Everything on the left is less, everything on the right is more. So if you look at 5, lahat ng mga nodes na nasa left niya is less than 5. So we have 1 and 3. Everything na nasa right is more than 5. So we have 7, 10, 9, and 12. Okay? And if you look at subtrees of the binary search tree, dapat ganun din yung property na makikita natin. So if you look at 10, everything on the left is less than 10, greater than 10, less than 3. Of course, wala nang nandito sa right side. Pero, yeah. So, yun yung binary search tree property. For a given sequence of numbers or for a given set of items, there are a lot of ways how to store this. So, this is just one. I can have this tree, left-leaning tree. And then, if it's a right-leaning tree, I can have this tree. Okay? So, it's also a legitimate binary search tree because it obeys the property. Okay? There are several operations on binary search trees. The first operation is, of course, searching. We can search in a binary search tree. So, for example, if our representation is this one, if we will look for item number 1, we know that we can see number 1 um, on the left side of the tree kasi 5 yung root node natin. Okay? So, if we look at number 3, alam natin na nasa left side lang din tayo titingin. Okay? So, generally, if you will use a binary search tree, you don't need to check all possible contents of the binary search tree. Our next operation is insertion. The way how we do it in binary search trees is to, number 1, search for the key as if it's there, and then kapag hindi siya nag-exist, insert at leaf where search is terminated. Okay, so insertion operation is search plus insert. Okay, this is to make sure that you will insert the new item dun sa appropriate location of the item in the binary search tree. So for deletion, the easiest type of deletion is deleting key at a leaf node because walang anak si leaf na kailangan mong ipamana sa other nodes. If you will delete a key na may single node, you need to have a way how to have a new parent for the now orphaned child, and ganun din with 2 children. So, the 3 operations are largely dependent on search because for deletion, of course, before you delete the node, you also need to search kung nasan siya nakalagay. So, search and then delete. For insertion, search and then insert. So, the efficiency depends actually on the height of the tree. So, just to give you an idea for searching, kanina, we are looking for item number 1. And to search for item number 1 in the given binary search tree, ang ginawa lang natin is to traverse the tree from root node to the location. If hindi siya nag-exist, for example, if we will look for item number 2, okay, 5, less than 5 si 2, okay, 3, less than 3 si 2. So, nung nakita niya 1 and 1 is already a leaf node, alam niya na hindi nag-exist si 2. So, the running time for searching is the height of the tree. So, kapag nakarating na siya sa leaf at wala ng item doon, then the search will stop. Okay, so, okay, depends on the tree height. So, if we look at other binary search trees na nasa worst case scenario, the right leaning tree and the left leaning tree, if you will search for item number 1 here, and you start sa root node, you need to traverse the height of the tree and then parang nag-linear search ka na rin dun sa sequence of elements. And the worst possible key naman dito is the highest number, which is 12. So, if you look for 12 starting from 1, you also need to traverse all the nodes. So, hindi tayo nakapag-maximize by using a binary search tree. That is why may ina-introduce na bagong type ng data structure, and that is balanced search tree. Okay, so ang goal kasi natin is to make a binary search tree that is as much as possible parang compact with respect to height. So as much as possible pantay yung nasa left and pantay din yung nasa right. So for the balanced binary search trees, may mga several types pa. And for our example, we will just explain yung tinatawag na AVL tree. Okay? So, again, the main reason why we wanted to have balanced search trees is to improve the running time of search, or in general, different operations on binary search trees. Kasi it can also have theta of n na worst case efficiency. So, ito yung try nating iiwasan. So, ito yung gusto nating maiwasan. So, as much as possible, gusto nating makapag-achieve ng log n. So, ang gagawin is to maintain an additional property, and that property is being a balanced tree. Okay, so how can we say that tree is balanced? One example of a balanced tree ay yung mga tinatawag na AVL trees. So by definition, an AVL tree is a binary search tree, so meaning everything on the left is less, everything on the right is more than the value of that key, with an extra property. And that extra property is this statement: for every node in the AVL tree, the difference between the heights of its left and right subtrees, yun yung tinatawag na balance factor. Dapat yung balance factor nung every node of the AVL tree is at most 1. Okay? So, let's look at this example. And to say that this tree is balanced, sabi niya dito, for every node. So, you get the balance factor of every node and then check kung may lalagpas sa 1 or may lalagpas sa -1. Okay, so how can we compute the balance factor? Let's start with the simple one. If we have a leaf node, okay, so we have 2, 8, and 12. If we have a leaf node, the balanced factor is 0 because wala na siyang nasa left and right. So technically, the difference between left and right ay 0 kasi pantay kapag leaf. If we have, let's say, this one with one child, the balance factor is 1 because you have a subtree na ang length ay 1 on the left side and an empty right subtree. So you have 1 minus 0. So we have a balance factor of 1. And then for this node, we have 2 minus 2. So that's 0. So balanced itong node na to. And then, if we look at the opposite side, the right subtree is 0 minus 1, so you have a balance factor of -1, and so on. Okay, so for this node, you have a subtree of length 1, 2, 3, and then you have a right subtree of length 1, 2, so that's 3 minus 2, you have 1. Okay? So, if you look at every balance factor in this example, wala tayong balance factor na less than -1 and more than 1. Okay? And in contrast, we have an unbalanced. So, for this key, you have a subtree of length 1, 2, 3, and a right subtree of length 1. So you have 3 minus 1, that's 2. Okay? So, kapag meron lang at least isa na node na may balance factor na hindi between -1 and 1, then that is an unbalanced tree. Okay? So, this is an AVL tree, while this is not an AVL tree. Our next question is, given an unbalanced tree, how can we transform this to make it a balanced tree? And yung manner of doing it is by rotation. So may mga different types of rotation. Mainly, there are two. May single rotation and merong double rotation. For the single rotation, we can have either a right rotation or a left rotation. For this example, we have a single right rotation. Okay, so from this unbalanced tree, from the single right rotation, we can get this balanced tree. The second type of rotation is a double rotation. And the double rotation is a sequence of a left-right rotation or a sequence of a right-left rotation. In this example, we are showing a left then right rotation. From this unbalanced tree, you can get this balanced tree on the right side. Okay, so as I mentioned a while ago, we used binary search trees for dynamic dataset. Yung mga dynamic dataset na yon ay may input that changes through time. So there is a sequence of insertion, there could be a sequence of insertion, deletion, and so on. So nagbabago yung content ng binary search tree natin. And we can construct an evil tree making sure that for each instance of the sequence, we can have a representation that is a binary search tree and a binary search tree that is balanced. Okay, so suppose we have a sequence of inserts. So we start with 5. Okay, so 5. This is an AVL with content equal to 5. And since isa lang naman yung content, we can have a balance factor of 0 since wala naman siyang left and right subtree. If we insert 6, we compare, again, if we insert an element in a binary search tree, we search as if nandun si 6 and then we insert. So, if we will look for 6, given this subtree, ang lalagyan ni 6 is on the right side of this node. So, since wala namang laman, then insert 6. And then compute for the balance factor. Since swak naman siya dun sa condition ng AVL, then we don't need to do anything. Okay, so kapag dumating si 8, again, search where we will put 8. So 8 is greater than 5. 8 is greater than 6. So we put 8 sa right child ni 6. So we have this. We compute the balance factor. Pagka-compute natin ng balance factor, merong isang node that makes it an unbalanced tree. So, naging negative to na. What we need to do is to transform this tree and rotate it to the left to make it a balanced tree. So, if we rotate this to the left, we need to recompute the balance factor, and since we have this as the balance factor, then it's already a legitimate AVL. Okay. So that is the AVL if we have 5, 6, and 8. So this slide is just to analyze the running time complexity of utilizing AVL as our representation for the sequence of numbers. If we will search or insert, the running time is O of log n. Since insertion is search plus constant time, it's still O of log n. For deletion naman, it's search plus deletion. Pero the deletion is more complicated than the insertion kasi you need to transfer the orphaned children, so medyo mas complicated, but the running time is still O of log n. The disadvantage for AVL tree is magkakaroon tayo ng frequent rotation and computation of the balance factor to maintain that the tree is still balanced despite having a dynamic content. So, if we compare this with a regular binary search tree, worst case scenario na, yung log n, pero ang worst case scenario, if we have a generic binary search tree, ay O of n. So, mas nakakatipid tayo sa running time for AVL trees. So, this is an example of a representation change for a problem. If we change the representation, sa case na to, we use an AVL tree to represent the data or the input, we were able to obtain a better running time efficiency. Okay, so konti na lang. This is the last type of transformation called problem reduction. So we are already considering two different problems dito. The original problem and the problem kung saan natin nire-reduce yung problem natin. So the idea here is to solve a problem by transforming it into a different problem for which an algorithm is already available. To be of practical value, of course, yung dapat problem na kung saan natin nire-reduce yung original problem natin is not a harder problem. Dapat easier problem siya. Technically po pwede naman talaga yun, pero ayaw natin pahirapan yung problema natin. We wanted to have an easier problem variant so that we can get advantage of this transform and conquer. I'll just give some of the few examples. Okay. So for example, we have two problems, LCM and GCD. LCM here is the least common multiplier of two numbers m and n, and to be able to solve LCM, we can compute it by first solving the GCD. And then we can get the LCM of m and n from the GCD by using the equation na nandito sa baba. Okay. So if this is well known, so it's just a matter of dividing this number over the computed GCD of m and n. Then you can get the LCM of m and n. The second example is counting number of paths of length n in a given graph by raising the graph's adjacency matrix to the nth power. Okay, so the original problem is counting number of paths of length n. And the reduced problem is getting the nth power of an adjacency matrix. The third example, we can always transform a maximization problem to its minimization counterpart and vice versa. Another example is by modeling the problem into a linear programming model and then using the linear programming approaches to solve the problem. Pero yung key doon is how you will be able to model your original problem or your combinatorial problem to a linear programming definition. And for the last example, we can actually use problem reduction to well-known graph problems. So we'll see more of this in the next 2 weeks.